Hello everyone, we want to do another word problem, an application question in the unit of polynomial equations. So there is a rectangular box with an open top that is to be made in the following way. That's the box, it's open top, and it says a piece of cardboard 20 centimeters by 30 centimeters has a small square cut from each corner, and then the edges are folded vertically. What should be the smallest size of the squares cut out if the box is to have a volume of 1008 cubic centimeters? This is the cardboard, okay? You buy it from the store, 30 centimeters by 20 centimeters. That's very clear. Now what we do, we grab a pair of scissors and we cut 4 squares from the corners. We cut this square here at the corner, we cut this one and throw it away, okay? When you throw them away, you end up with the remaining part of the cardboard. So you use these dashed lines and you fold the cardboard vertically up. When you fold these up, you are generating the walls of the box. And the box is going to look like something like this. It's an open top box. Now the question is, when you're cutting those squares from the corners, what should be the dimensions of those squares that you are cutting, such that the final product, which is this box, have a volume of 1008 cubic centimeters. So that's what the question is. It's like another engineering kind of question. Okay. So because we don't know what is the dimensions of these squares, we don't know. It should be like 2 by 2 kind of square that we have to cut from the corners. Should it be 3 by 3, 4 by 4? We don't know. So we're going to call it x. Okay, so x represents the size of this square, the side length of the square that needs to be cut from the 4 corners. Okay, but when you bend it up, actually, when you fold it up, this x actually becomes the height of the box, if you use your imagination a little bit. So this is actually the x when you fold it up. So the height of the box is actually our independent variable x. And with regards to the length of the box, if we cut this square out, we cut the other one out. So 1x from the left side, 1x from the right side is cut out. The total was 30. So that means that 30 minus 2x is what is left in the middle. And that will be the length of the open top box. And for this width part from here, we have a total width of 20 centimeters. You're cutting x from the top and bottom, so that would be 20 minus 2x, and that becomes the width of your box. So the width is 20 minus 2x, and the length is 30 minus 2x. And we know that the volume of any rectangular prism is length times width times height. So we're going to multiply x by 30 minus 2x by 20 minus 2x, and we end up with this volume function, we can say. And it's a volume function of x, which is the height of the box. And now we know that the volume is supposed to be 1008. So we're going to substitute 1008 here, and then we're going to multiply 30x minus 2x squared, and then 20 minus 2x. And then we have to do the fold and multiply these binomials. And then if you rearrange the terms and you simplify, you will end up with the following equation. So I'm skipping a couple of steps. I assume you know how to expand. I assume you know how to collect like terms and simplify. So you end up with x cubed minus 25x squared plus 150x minus 252 equals 0. Okay? So you end up with a cubic equation once again. Now, how can we solve this cubic equation? Well, we use factoring. But how do you do that? We can use factor theorem. Okay? In order to do that, you need to find the divisors of 252. And this time, it's a large number. So plus minus 1, plus minus 2, and then plus minus 4, and then 7, 3, 6, 9, and then we have 12 and 18, and quite frankly, there's a lot of, divisors, okay? Many of them are big numbers, but we don't care about those because we just want to find x, right? So we don't believe that x would be like 18. Um, Imagine the total width is 20. How could x be 18? So we know that. So that's why I put dot dot dot. We don't write all of them because we don't believe any of those would be the answer. So perhaps one of these smaller integer values would be the answer. Now, if this is your f of x, you try f at 3, and that would be 0. So x minus 3 is a factor of f of x. Okay, so we're going to divide by x minus 3. I've already done the work here using synthetic division to save some time, and I got the quotient, x squared minus 22x plus 84. Those who are interested, they have to do the calculations by themselves, and they can check with this answer right here. So we will end up with x minus 3 times that quotient, x squared minus 22x plus 84 equals 0. So we succeeded in factoring the cubic polynomial, and using factor theorem, we factored it. Now we're going to say either x minus 3 is 0 or the quadratic trinomial equals 0. And this comes from zero product property. So x equals 3 centimeters, or now we have to solve this quadratic equation. So if you do the calculation, you end up with a simplified answer of 11 plus minus square root of 37. Okay, so once with the plus, once with the minus, we're going to have two answers. So this is one of the roots, this is the other. So let me count here. We have x sub 1, x sub 2, x sub 3. There are three x values we found that they satisfy this equation, okay? But is it true that all of these are like admissible? We have to see. This one is approximately 17.08 if you use a calculator, and this one is 11 minus square root of 37 is roughly 4.92, okay? So centimeters and centimeters. Now, if you look at x, x like cannot be more than 10. Even 10 it can't be because the whole width is 20. Half of it is 10. So if you cut 10 from the top, 10 from the bottom, then the whole width will be gone. So theoretically speaking, x will be less than 10. Okay, not equal to 10 for sure. So we're going to say x, basically, we're going to say x has to be less than 10 for sure, okay? And it can be negative, therefore we say it has to be greater than or equal to 0. So this is some sort of domain for our variable. In application problems, this happens that we have to state some restrictions. This is the restriction we have for our variable x, which represents the height of the box. Okay, so if that's the case, if you're saying x must be less than 10, because it doesn't make sense to be more than 10, the box would not even exist, for heaven's sake. So in that case, this 17.08 will be an inadmissible solution. So we're going to say this is inadmissible. So we can't accept this. But 4.92 is actually less than 10. So that's a possibility. And 3 is also a possibility because they both lie within the domain of x. So nothing is wrong with x being 4.92 or x being 3 centimeters. So if x is 4.92, so height is 4.92 centimeters, then the width would be 20 minus 2x. Using a calculator, it will be 10.17 centimeters. Because you plug in here 20 minus 2 times 4.92. So it gives you 10.17. And the length would be 20.16 centimeters as per my calculator. So this would be the dimensions of that box, which would have the same volume of 1008, okay? And the height, of course, is within 0 and 10, and it satisfies the restriction. And it is possible to have such box actually with this height. The other solution was 3 centimeters. So the height is 3 centimeters, and the width is going to be 20 minus 2x. So 20 minus 6 is going to be 14 centimeters, and 30 minus 6 is going to be 20 how much? 24 centimeters, right? 24. So this would be another combination of solution, which is like reasonable, because the height is 3 centimeters and it's less than 10 and it's positive. So we can have a box with a height of 3 centimeters, and then the width and the length would be 24 and 14. The volume would be 1008, satisfies all the conditions. And this is just another possibility we came up with. So basically the question has two solutions so far. So far, it has two solutions. Both are admissible. The only inadmissible answer was 17.08. Okay. Now we read the question carefully. It says, what should be the smallest size? Somebody has underlined the word smallest. What is the smallest size of the squares cut out if the box is to have a volume of that much? So smallest. So this is 4.92. That is 3 centimeters. Both are admissible. But the question says the smallest. So the smallest height has to be 3 centimeters. That's the final answer. And that's why I put it inside the box. Okay. So we're going to say the smallest, okay, the smallest height of the box should be 3 centimeters. That is the squares cut out from the corners must be 3 by 3, 3 centimeter by 3 centimeter squares. Okay, so logically speaking, when you're doing an application question or a word problem, we always write a final closing statement, okay, or a paraphrase. And this is the sentence that we write, including the units of measurement, so that we actually answer the question, okay? So I hope you understood how we take care of these word problems, application questions. This is like number 3, I think I'm giving you. And I hope I answered the question of why, because we learned about what, and then we learned about how, and now we learned about why. Why do we learn all these mathematics that we learn? Because it has applications in real life, because you can solve many, many word problems in different fields, whether business, finances, engineering, medicine, you just name it, okay? In every field, it has applications. So keep practicing, and I think this unit is almost finished. We talked about what, how, why, nothing is left. And the next unit would be rational functions. Thank you.